Okay, it's recording. Good morning, everyone. Welcome to part one of lecture 13 of the course Quantum Theory in a Nutshell. Um, so today I want to continue on the discussion that we had yesterday. Unfortunately, in the end, there was a connection issue on your side. So I will just very briefly recap the end of last lecture so that we can continue with the discussion. And what we did yesterday was, uh, no, so today there is a break. I think 2 hours in a row is not good for an online lecture. So I'll give you the break, okay? Um, okay, so um, then we discussed yesterday different aspects of, how to write down an operator in a matrix form, and how do you really act with this operator on a cat, and also how do you compute the matrix elements of this operator. And we saw that you use this sandwich operator, namely you take the operator, you act with the operator on a cat, and then you act on the result with a bra, and then you get the ijth element of the matrix. And then I showed to you that if you define a cat which is the action of an operator on another cat, then you can and you expand these two sides of this equation in the same basis, then you can compute the coefficients of the new vector C prime in terms of the in terms of the old vector C and the elements of the matrices, the matrix, and this is the relation. And finally, we defined what is a Hermitian conjugate of an operator. So essentially, thinking of a matrix, and let's think of a 2x2 matrix, the Hermitian conjugate of the matrix A hat is denoted by A hat dagger, and you obtain that by taking the transpose of this matrix and taking the complex conjugate of each element. So this is the recipe that you have to use in order to obtain the Hermitian conjugate of a matrix. Okay. Then I just came back to this discussion of having a cat, which is defined by the action of a matrix on another cat. And I taught you how to extract the bra associated with this cat. So if now you want to compute the bra of C, so you want to compute this guy, you have to write bra B. So you first transform the cat B into a bra, and then you multiply it by the Hermitian conjugate of the matrix B, so B dagger. So if I give you a cat C, which is B times B, then the bra C will be the bra B times the B dagger, okay? That's very important. When you take the dual of a vector, namely when you take the bra of a vector, you have to take the dagger of the matrix, okay? Okay, so I also told you that you can prove, and I think this was the moment that the connection was really starting, already actually being bad for you. If you have two matrices, A and B, and you take the product of these two matrices, this will be another matrix, okay? Now I can ask you, what is the Hermitian conjugate of this product of matrices? Well, you can prove that the dagger of product of AB is B dagger times A dagger. So you invert the order of the matrices and take the dagger of each one. And it is crucial that you invert the order because remember, matrices typically do not commute. So you cannot write the matrices in any order. There is an order that you have to obey. So when you take the dagger of a product, you first switch the order of the matrices and then take the dagger of each matrix. Okay? So this is how you take the dagger of a product. And now comes a very important definition, which is the following. If you have an operator A, and if every time that I say operator, you can think of it as a matrix to be concrete. So if you have an operator A, which satisfies the relation A is equal to the Hermitian conjugate of A, okay? So here I'm saying that if I perform this operation here, so if I take the dagger of this matrix, I get this new matrix. But it can happen that when you take the dagger of a matrix, the resulting matrix is equal to the first matrix. This can happen, okay? And I'm saying that if you have such a property, namely, if a matrix is equal to a dagger, then we call this matrix as a Hermitian matrix, okay? So a Hermitian matrix is a matrix that satisfies this property. The Hermitian conjugate of this matrix is equal to the matrix itself, okay? So let me just comment that if you have a matrix of the type A1, A2, A3, and A4, now if I take the Hermitian conjugate of this matrix, I will have A1 star, and then I'm transposing, so A2 comes to this place, and A3 comes to this place, and A4 remains here. And what I'm saying is that if this matrix is Hermitian, then this equality must hold, okay? And when you say that a matrix is equal to another matrix, you're saying that each element of each matrix is equal. So you're saying that A1 is equal to A1 star, A2 is equal to A3 star. See, I'm equating this guy with this guy. And then A3 is equal to A2 star. So you see that this equation is essentially the same as this equation. And A4 must be equal to A4 star. Okay, what is the conclusion of that? The conclusion is that the element A1 must be equal to the complex conjugate of itself. And we have seen that when a number is equal to its complex conjugate, then this number is just a real number, right? Real numbers satisfy this property. If you take the complex conjugate of a real number, it's just the real number itself. Then A2 must be the complex conjugate of A3. So if I plug a number here, A2, the number that should appear here, A3, must be the complex conjugate of A2, okay? And A4 must be equal to A4 star. And again, as we concluded for A1, A4 must be a real number, okay? So what is the conclusion of that? Well, the conclusion is that a Hermitian matrix will have this structure here. It will have a real number, x. It will have another real number, y, in the diagonal of the matrix. And in the off-diagonal parts, you're going to have something of the form A plus IB. And the other off-diagonal term must be the complex conjugate of this term here. So it must be A minus IB. So this is the general structure of a Hermitian matrix. Okay, the diagonal is real, and the terms that are off diagonal must be the complex conjugate of each other. So if I give you this matrix, for instance, 2 minus 3i, 3i, and 4, I can ask you, is this matrix a Hermitian matrix? Yes or no? Paul said yes, 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 yes. This is a Hermitian matrix. The diagonal term is real, and the off-diagonal terms are complex conjugate. Okay? And for instance, if you have now a matrix that has this structure, let's say 2, 4, and then you have 1 plus 2i and 1 plus 2i. Is this matrix Hermitian? Yes or no? No, it is not, right? Because the diagonal term is real. That's fine. That's good for a Hermitian matrix. But the off-diagonal terms, they are not the complex conjugate of each other. So this is not a Hermitian matrix. There is a particular property which is important, which is the following. So if you have a matrix of the form x, y, so these are real numbers, and I have something of the type C and C. Well, C is a terrible name, actually. So if I have something like M and M, where X, Y, and M are real numbers, okay? So everybody here is real. Is this matrix Hermitian, yes or no? Yes, it is Hermitian because you see the diagonal is made of real numbers, that's good, and the off-diagonal terms must be complex conjugate. But this is a real number, so the complex conjugate of a real number is just the same number. So the complex conjugate of M, if M is real, is just M. So this is a Hermitian matrix, and you see that every time that you have a real matrix that is symmetric, namely if I mirror the elements from here to this side and I get the same numbers, then this matrix will be Hermitian, okay? Very good. So I hope everyone now has a clear picture of what a Hermitian matrix is. So let me go back to the discussion of quantum mechanics, because what I am saying here about Hermitian matrix is just linear algebra, right? So I told you that the main goal of these discussions is to have postulates about observables. And this will answer the question that was posed yesterday on how to extract the AJs, namely the possible outcomes of a given experiment. And we also will discuss on how to obtain the states that give you always the same values with 100% of confidence. So there is a question by Seth, which is, that means that the off-diagonal entries are not strictly complex numbers. No, so the off-diagonal terms, so that all the entries of the matrix can be complex numbers in principle. And you see that the hermiticity imposes that the diagonal will be real numbers, and the off-diagonal must be complex numbers, which are complex conjugate. But of course, if you have a number, a complex number, which the imaginary part is 0, then this is just a real number. So this is a particular case, okay? So they must not, I mean, you don't need to have eyes on the off-diagonal terms, okay? Prince, A equals to A transpose only. Yes. So when M is belongs to the reals, then the condition that you wrote, A equals to the A transpose, means that the matrix is symmetric. And this is a condition to be Hermitian if you just have real entries. Okay? Good. Okay. Now let me continue with the discussion. So, we have defined, I think yesterday or 2 lectures ago, the expectation value of an observable A in a given state U. Okay, and this state is a state that I don't know what is the polarization. Maybe it's not even a state with well-defined polarization. Okay, but the expectation value of the operator A was defined by this quantity, right? I take the bra of U, I insert the operator A, and I act on the cat U, okay? But you see that the expectation value, if you remember, the expectation value, the expectation value that I defined here is the probability of getting the outcome AJ times the outcome AJ. So the outcome is a real number, right? You measure in the lab a real number, and the probability is also a real number. So the expectation value of an operator in a given state U must be a real number, okay? So this is a property. Now I have this definition of the expectation value, and I say, well, this this number must be real, okay? So what this means? This means that if I take the complex conjugate of this number, so this is just a number, so I can take the complex conjugate of this number, and you see that if I take the complex conjugate of this number, this is equivalent, as we have seen. So you remember this property that AB is equal to BA star, right? This is a general property. So you see that I can do the following here. I can write this product, this scalar product, as the bra U acting on A U, right? I'm just looking at this particular order of operations. First, I multiply the cat by the matrix, and then the result of this, which will be a cat, I take the scalar product with U. So I can now reverse the order of the scalar product as I just showed to you. And when I reverse, I have to define the bra associated with this vector, right? The bra associated with this vector, just following this rule here, will be bra U and then A dagger, right? This is the bra associated with this cat, right? And then I multiply by this bra that will become a cat, U, okay? So I just took this expression and I reversed the order of the operations, all right? But remember, when I reverse the order on a scalar product in a complex vector space, I have to take the complex conjugate. So this is what is written here. I start with this scalar product, and now I'm just exchanging the order of the vectors. So I take this first vector, which is A acting on U, and I transform that into a bra, which will become bra U times A dagger, and then I multiply by the cat U. And of course, since I'm exchanging the orders, I have to put the complex conjugate here. Okay? So first, to be consistent, this must have a hat. But now, you see that if I assume, okay, that A dagger is equal to A, in other words, if I assume that the operator is Hermitian, then I can just remove the dagger here, right? Because A is equal to a dagger. So I remove the dagger and I get to this conclusion. Okay? In other words, you can not assume, maybe you don't want to assume that A is Hermitian. So you say, from this side to this side, I'm just reversing the order of the vectors. But this equality here, so this number being equal to this number, is just a request that I make that the expectation value of A must be a real quantity. Okay? So if this is real, then it must be equal to its complex conjugate. But it is also equal to this thing. Okay? So the only possibility that this can happen is if A is equal to a dagger. So if the matrix is Hermitian. So what I'm concluding from this brief discussion is that if I want to measure or if I want to compute the expectation value of an observable in a given state U, I have to have, for this to be real, I have to have that the matrix A is Hermitian. Okay? So an observable will have real valued expectation value, will be, an observable will have real expectation value if the matrix is Hermitian. Okay? So, with that discussion, we can write the following postulate, which is very important. So, an observable quantity, so if I'm associating a physical quantity, which I call an observable in quantum mechanics, to an operator, it must be represented by a Hermitian operator. Okay? So if you want to define an observable in quantum mechanics, you need to define it as a Hermitian operator. Okay? If the operator is not Hermitian, then it cannot define, in principle, an observable. Okay? So every time that I speak about an observable, namely polarization or energy or position, momentum, angular momentum, all of that, these will be represented by a Hermitian operator. Okay? Good. So we have seen that if you have an operator A, right, which is associated with some physical quantity that can have two possible outcomes, A1 and A2, we have seen that you can represent that using the projectors. Okay? So you have to write the outcome A1 multiplied by the projector associated with A1, which is formed by the states that will always give to you the value A1 if you measure them, plus A2 times the projector pi 2. Again, this should be consistent, and I must put a hat here. Okay, and we have seen that these projectors are just the outer product of these objects, EJ, EJ. So this is how you represent an operator, and we just saw from this statement here that this operator must be Hermitian if this is an observable. And we also saw that these vectors E1 and E2, they form an orthonormal basis, okay? So they are orthogonal if you take the scalar product between E1 and E2, and they are 1 if you take the scalar product between E1, E1 and E2, E2. So now I can ask the following. If I take this representation of the operator A, written as outcome times the outer product of these vectors that form a basis, I can ask the question, what is the result of acting with the matrix A hat on a vector EI? Okay? So, what I'm doing here, well, I'm just applying this matrix to this vector. But this matrix A hat, as we just saw, can be represented as the sum of AJ and the outer product AJ. Okay? So you're going to have this structure here, AJ, acting on EI. Okay? So when you, again, this is the action of the outer product. So you have to glue these two guys, and this will give to you EJ, EI times EJ. Okay? But what is the result of the scalar product between EJ, EI? Do you know the answer? Is Mahmoud said 0. Now, so your name is very difficult for me. Let me. Andri. Yeah, it's too difficult. Andrian. Can you say your name for me?
Andrea Sana.
I'm not sure.
Nandi, just Nandi.
Andy, okay, that's easy. Okay. So very good. Sila says 0 or 1, delta Ji, 1, 0, if, okay. So the correct answer is EJ scalar with EI is delta Ij. Namely, it is 0 if J is different from I. And you see you're summing over J, so J will take different values. So when J is different from I, this is 0. And when J is equal to I, this will be 1. So this is represented by the Kronecker delta, delta Ij. And I will have the following result. I will have that I will have a sum I'm summing over 1 and 2. Then I'll have EJ delta Ij. But you see that delta Ij is just a number. It is either 1 or 0. And I'm summing over J equals to 1. And, I'm summing over J, which goes from 1 to 2. So J will be 1 or 2 in the sum. And this guy here will have the value that J has when this delta is 1. So this sum will filter the value of J that agrees with I. Okay. So if I is 1, then it will filter J equals to 1. If I equals to 2, it will filter the value J equals to 2 because the other one will be 0. So the result of this sum is that just the terms that J is equal to I are going to survive, right? So I have to replace J's by I's everywhere and kill the sum. So these will be AI, EI. Okay? So what I'm saying here is that when I apply a hat to the vector EI, I get little a I, EI. little ai is nothing but the outcome that the one possible outcome that you see in the experiment. Okay? So Mahmoud is asking, why did you kill the sum? Well, I'm summing over 1 and 2. So when j takes the same value as I, then I will have 1 for the delta. And if otherwise, j will differ from I, and then this delta will be 0. Okay? So the only term in this sum that will survive is the term that j is equal to I. So I selected this term, wrote here, and all the others will be 0 because j will be different from I. Okay? So the sum is reduced to a single term because all of them are 0. Okay. So look at this equation. I'm saying that an operator acts on a vector ei. It gives me a number ai times the same vector. What is this equation? You learned that in linear algebra. This equation tells you if you act with an operator on a vector, you get back the same vector multiplied by a number. Do you remember which equation is that? No? Yes? Yeah.
Eigenvalue.
Exactly. So this is the equation that defines to you what are the eigenvectors of A, and the eigenvectors of A are the vectors that when you act with A on them, this gives to you a number times the same vector. So this is an eigenvector, and the number is the eigenvalue. Okay? So what this equation is showing is that the operator, which is the observable, is represented by a Hermitian operator, A hat. The vectors that have well-defined measurements, namely, if the system is in the state EI, I have 100% confidence that the outcome will be AI. So those vectors are eigenvectors of A, and the possible values that I'll measure on the lab are eigenvalues of this operator. This is very abstract, but now you have a systematic way of computing what are the states that are well defined for a measurement and what are the possible outcomes of this measurement. The possible values of a measurement will be the eigenvalues of the operator that represents the observable. So if A, for instance, is a matrix that represents the energy of the system, then the eigenvalues of this matrix will be the possible values of energy that I can extract from the system. And EI will be the eigenvector, and in other words, will be the state of well-defined energy. So if I measure energy for this state, I'll always get back AI. Okay? Few comments. Yes, I can repeat because this is important and I know that it's non-trivial. So what I'm saying here is that, so I started by writing a hat as an observable in this way, right? I expanded as the outcomes times this outer product. And with this manipulation here, I'm concluding that actually these vectors EI, they are eigenvectors of this operator. And the outcomes of the measurement, AJs, they are eigenvalues of this operator. So if you define an operator that represents an observable, you can extract just from the operator itself what are the possible values that you're going to measure in an experiment. So if you take an operator and compute the eigenvalues, those are the values that will show up in your detector, in your measurement device. Of course, I'm not telling you that you're going to measure always the same value, but you're going to measure one of those values with some probability. But the states which have well-defined values, namely those states that if the system is in one of those states, you always measure the system with the same value, those states are eigenvectors of the operator. Okay? So typically, since they are also states in a quantum system, instead of calling them eigenvectors, we call them eigenstates. But this is just a name. Okay? So you can see eigenvectors or eigenstates in quantum mechanics, and they mean the same. Okay? Hope this clarifies a bit. But this is going to get, you're going to get more used to that. Okay? So now I will write two more postulates about observables. Well, the first postulate is the possible outcomes of the measurement of an observable A hat are the eigenvalues of A. Okay? And postulate 5 says that the states for which A has the values A1 or A2 with probability, I should say with probability 1, are the corresponding eigenvectors or eigenstates E1 and E2. Okay? So, this explains a lot. For instance, we have seen that in quantum mechanics, we can see, for instance, this binary measurements. So you can have either yes or no as the outcome of your measurement. But you can also have a discrete set of values for your observable. So sometimes you measure something, and in classical physics, most of the phenomena can have a continuum set of values. And for quantum mechanics, it happens quite often that your observable will be such that the possible outcomes of your experiment are just form a finite set of possible values. And the reason for that is the following. So if we're dealing with a two-level system, for instance, as we are, you know that you represent operators as 2x2 matrices, and you know that a 2x2 matrix will have two eigenvectors and two eigenvalues. So if you measure an observable that is represented by a 2x2 matrix, you know that you're going to measure a quantity that has two possible values. Okay? So this way of representing an observable makes clear why we have situations where you are going to measure just a finite set of possible values for the measurement. All right? This is extremely important. I mean, understanding that in quantum mechanics, you're really talking about observables as operators that act on states, which are vectors. Okay? And the thing that you measure, the number that you read on your measurement device is an eigenvalue of this operator. Okay. But there is one final thing that, well, it's a bit, we already touched on that, but let me just make it clear, which is the following. If you have observables as Hermitian operators, and the possible outcomes in the experiment are the eigenvalues of the operator, then you better have an operator that has real eigenvalues, right? Because if the operator has complex eigenvalues, then following this postulate number 4, you are going to say that you can measure an outcome which is a complex number. So you can say, well, if I have a matrix which represents an observable, and I compute the eigenvalues, and one of them is a complex number, then what I'm saying here is that this number will be a possible outcome of an experiment. And this is nonsense. I mean, your measurement device will report to you real numbers. But it turns out that Hermitian operators, as we discussed in the previous slide already, they have this very nice property, which is that a Hermitian operator has necessarily real eigenvalues. Okay? So if you have an operator which is Hermitian, and if you compute the eigenvalues of this operator, then they are going to be real numbers. And I mean, if you're curious about that, here is written a proof of that. So it's really very simple proof. But I don't want to explain details that, because this is something that you can easily go through. It's very simple and tells you that for every Hermitian operator, all the eigenvalues will be real numbers. Okay? And there is another important result in linear algebra, which is the so-called spectral decomposition of an operator. That says that a Hermitian operator can be written as the sum of its eigenvalues times the outer product of its eigenvectors. So this is a theorem in linear algebra, and you see that this is exactly what we have seen before. We constructed this operator from the discussions that we had before, and if you rely on the machinery of linear algebra, this follows naturally, that the observable will be represented as the possible outcome of your measurement, and that it must be multiplied by the projectors formed by the eigenvectors of the operator. Okay, so in this representation, namely, if you're really expanding the operator in the basis of its eigenvectors, then the operator has a diagonal form. So this is a very useful result. So if you know the eigenvectors and the eigenvalues of A, you know that you can make a transformation in the operator and change the basis of this operator in such a way that it becomes a diagonal matrix, and with entries A1 and A2. And since this must be Hermitian, then these numbers must be real. Okay. Let me see the chat. Oh, sorry. Let me. Is it pi hat or just pi? Oh, it should be pi hat. You're right. So this is a problem, because at some point you're going to get used to these operators, and you're going to forget about these hats. I mean, it will be automatic to you that these are operators. But when you're learning, it's useful to put these hats to remind you that these are matrices, and you cannot commute them with things in general. So it's useful to write this hat. But at some point, you just ignore that. And that's why sometimes I will forget these hats. but it's good that you pointed out. Then there is a question, must the Hermitian operator only be a 2 by 2 matrix? No, not at all. I mean, if you have an n by n matrix, it can be a Hermitian matrix. You just take the transpose of this matrix, the complex conjugate of each element, and equate that to the matrix itself. This, and I mean, you can have a Hermitian n by n matrix. Moreover, you can have more abstract operators which are Hermitian. For instance, there are operators that you don't write in terms of matrices, right? So for instance, you know already an operator that is the derivative operator, right? So the derivative operator is an operator that acts on functions and gives you the derivative of the function, right? So this guy here can be faced as an operator. It acts on a function and gives you back another function, as matrices act on a vector and gives you back another vector, okay? So the derivative is an operator. And you can ask yourself if the derivative is a Hermitian or not, is a Hermitian operator or not. We're going to get to that at some point. Okay, so when you talk about operators, you can think of them as being objects that act on a space, on a linear space, and gives you back another element of this space. So when you have n eigenvectors, well, this just generalizes as, I mean, in the simple way. So if you have an n by n matrix, let me call it, I don't know, H, and you compute the eigenvalues of H and the eigenvectors of H, then you can expand this as sum over I equals to 1 up to n. So this is an n by n matrix, so it will have n eigenvalues. And then you write the eigenvalues, let me call them lambda I times the eigenvectors, and let me call the eigenvectors as being, I don't know, small h, hi. So this is the spectral decomposition of the operator H hat using the basis of eigenvectors of H and eigenvalues of H. Is that clear, Grace? Yeah. There is another thing, which is you said that Hermitian matrix should have the diagonal real. No, this is a general thing. So any Hermitian matrix should have the elements of the main diagonal as real elements. What Mahmoud asked, what if we made more than one measurement? Oh, so sorry, it was not clear, the explanation. So you are not sure about what? About the diagonal of the matrix being real? So if you have a, let's say, n by n matrix, you're going to have something like A1, A2, up to AN, right? And here you're going to have some elements that I do not write, and here you're going to have some elements that I do not write. If the matrix is Hermitian, then all these A's, which are part of the diagonal, must be real. Okay? You can show that, as we just showed for 2 by 2 matrices. It generalizes immediately. Okay? Good. Then there is a question by Mahmoud, which is, what if we made more than one measurements on the same state? Is the result the same? So if we're measuring, for instance, the observable A, and the state is an eigenvector of the observable A, then you can measure how many times you want. The outcome will be the eigenvalue corresponding to this eigenvector. And yeah, so you're going to measure the same value every time. If the state that you're looking at is an eigenstate of the observable that you're measuring. Okay. Good. So we are already starting talking like people that really know quantum mechanics. You're talking about eigenstates, and you're talking about observables. And let me say that the spectral decomposition is a beautiful theorem in linear algebra that we use a lot. And also, let me remind you that I use the word spectral here because in mathematics, when you know the eigenvalues of an operator, you say that you know the spectrum of the operator. Okay? So when I ask you what is the spectrum of an operator, I'm asking you what are the eigenvalues of this operator. And since this decomposition relies on the eigenvalues and eigenvectors, we call this the spectral decomposition. Okay? Just to refresh your mind about that. Okay, so I think I'll stop now for the break. Then I'll just tell you after the break a concrete example of an observable, and then we are going to move to the uncertainty relations. Okay, so thank you for your attention. See you in 10 minutes, and yeah, have a good break. Bye-bye.